Lesson 4 is going to be on percent error. Today's lesson is going to be on accuracy versus precision and then calculating the percent of error. So accuracy is how close a measurement is to its actual or true value. Precision is how close the measured values are to each other. So if you can see on the targets on the bottom, the first target all the way to the left has high accuracy and high precision because it's closest to the true value and it's consistently close. Then you go all the way to the right and this has low accuracy, low precision because first, we're not very close to the target, and second, they're random and spread throughout the entire target.
So another way to think about accuracy and precision is when you're doing basketball or any type of sport. If a player always makes a basket, even though he strikes different portions of the rim, he has a high degree of accuracy. If he does not make many baskets but always strikes the same portion of the rim, he has a high degree of precision. A player who throws free throws that always make the basket that exact same way has a high degree of both accuracy and precision. In science, we're going to be talking about the fact that we should always measure things twice. If you take a measurement of a mass of a 50-gram sample, you might get values like 47.5, 47.6, 47.5, and 47.7. Your scale may be precise because the numbers are not fluctuating, but it's not accurate because you know it's 50 grams. But if your scale gives you values of like 49.8, 50.5, 51, and 49.6, it is more accurate because it's closer to 50, but because the numbers are varying so much, it is not precise. The more precise scale would be better to use in lab, providing that you make an adjustment for this error. This is why you should always measure things twice. Sometimes the electronic readers are not accurate.
So on reference table T, we're going to look at percent error. Accuracy is essential in chemistry, so we always are going to measure our percent error in a lab. So here's a formula. Percent error is equal to the measured value minus the accepted value divided by the accepted value multiplied by 100 because it's a percent. So measured value is the quantitative value you measure in an experiment. It's the one that's coming from you. Accepted value is the one that is 100% accurate, precise, and it's again a quantitative value that you want. You can get that value either from your reference table, table S, or from us. Now, when you calculate percent error and you get a positive value, that means you measured or created more than was accepted. If you measure a negative percent value, you are measured or you have created less than what was acceptable.
So steps to reading these problems is obviously read the question. Underline all of the quantitative values. Those are going to be things that are measurements. Plug the quantitative values into the percent error formula. And then just like math class, you have to do PEMDAS. Parentheses, exponents, multiplication, division, addition, and subtraction in that order. So the first thing you do, you subtract the numerators. Then you simplify that fraction. Multiply it by 100 and make sure your answer is written as a percentage. So let's try this problem. I want you guys to pause the video and then try.
So now that you've tried this, hopefully you took that 3.87 grams per milliliter and you plugged it into the formula as the measured value. Now it says actual density was 3.66, so that is your accepted value. You put that wherever it says accepted value. Then you work on the numerators first. 3.87 minus 3.66, divide by 3.66, multiply by 100, and you get positive 5.74%.
This means that the measured value was more than the accepted value. And just going back and looking at the densities that were determined, the density the lab technician determined was more than what it should have been, hence the positive number.